In an earlier lesson, we defined what a continuous function is. Intuitively, a function is continuous at a point if the graph of that function doesn't have a hole nor a jump or break in the graph at the point. Let's define what it means to be continuous on an interval. A function is continuous on an interval if and only if it is continuous at every point of the interval. So a function that's continuous on an interval will not have any holes or breaks over the whole interval. We simply call a function continuous if it is continuous at every point of its domain. Now, we've already encountered some special types of functions that are continuous, such as polynomials. They are continuous at every point on their domain. Let's see some other examples of continuous functions. Suppose you have two functions f and g that are continuous at a point c. Then the following combinations of f and g are also continuous at c. F plus g, the sum of the two functions, will be continuous. If you subtract g from f, if you subtract one continuous function from another, the result will be a continuous function at c. If you have a continuous function and you multiply by a constant k, some any number k, then this function will still be continuous at c. The product of two continuous functions, f times g, will also be continuous. And the quotient, f divided by g, will be continuous at c as long as you're not dividing by 0, so as long as g of c does not equal 0. If you take the product of a continuous function, so the function f raised to a positive integer power n, this function will still be continuous at c. And square roots, or any nth root, provided that n is a positive integer and you're not ever taking an even root of a negative number, then the nth root of a continuous function f will still be continuous at c. So these examples of continuous functions are a consequence of all the limit laws that we saw in earlier lessons, because we know that continuous functions are defined by the limits. So if you have two continuous functions, f and g, when you combine them in just about any standard way of the standard operations, you will still have a continuous function at c. Some more functions that are continuous. A polynomial function is continuous on its domain. And since polynomial functions are defined for all real numbers, this is one reason why polynomial functions are so nice. They're continuous on all real numbers. Rational functions, recall, are defined as a polynomial divided by a polynomial. So we saw that the quotient of two continuous functions is continuous as long as the function is defined. So you have to watch out for when the denominator of a rational function equals 0. That would be the only time you would have a discontinuity of a rational function. We can also combine continuous functions using composition. If f is continuous at a number a and g is continuous at f of a, the number f of a, then the composition function g composed with f will be continuous at a. So in other words, a continuous function of a continuous function is a continuous function. So the last statement that we just saw about the composition of continuous functions being continuous is a consequence of this fact. If f is continuous at the point b and the limit as x approaches a of g of x equals b, then the limit of f composed with g of x as x approaches a equals f of b. In other words, that equals f of the limit of g of x as x approaches a. So if you look at the last line of this statement, you notice that the limit is outside the function f on the left side. So you have the limit, and remember f is continuous at the point b. So if f is continuous, you can take the limit of a continuous function f, and then you can pull the limit inside the continuous function. Now the limit is on the inside, so you have f of the limit of g of x as x approaches a. So if f is a continuous function, you can pass the limit inside the the continuous function f. So let's see an example of this theorem. Suppose I want to evaluate the limit as x approaches pi over 2 of this composition function cosine of the quantity 2x plus sine of 3 pi over 2 plus x. So we know that trigonometric functions are continuous. If you think about sine and cosine, the graphs look like waves and there's no holes or breaks in the domain of sine or cosine. So since cosine is a continuous function everywhere, I can pass the limit inside the cosine function and obtain this. The cosine of the limit of 2x plus the limit of sine of 3 pi over 2 plus x as x approaches pi over 2. So this is a consequence of the previous statement with using the fact that cosine is continuous. Now consider this first limit here. The limit of 2x being a polynomial, I can evaluate this using direct substitution. So I would just get 2 times pi over 2, which reduces to pi, plus the limit of sine of some composition. Again, I can use the fact that sine is continuous to pull the limit inside the sine function. So I could obtain the sine of the limit of the inside function. And again, I'd have a polynomial, and I could just plug in pi over 2 for x on the inside to evaluate that limit. So in the first limit on the inside, the limit of 2x as x approaches pi over 2 reduces to pi. And on the second limit, when I bring the limit inside and then I plug in pi over 2 for x by direct substitution, I would get 3 pi over 2 plus pi over 2. That would give me 4 pi over 2, which would reduce to 2 pi. So that's how you would get sine of 2 pi. But we know that sine of 2 pi actually equals 0. So this quantity just simplifies to cosine of pi. And cosine of pi is -1. So we can evaluate complicated limits involving continuous functions by using this property that you can take the limit of a continuous function and pull the limit inside the continuous functions.